Good day, everyone, and welcome. Thank you for joining us. My name is Phil Conradi, the computer-aided engineering specialist at Metix. And today, myself and Evan Smith from QFinSoft are going to be introducing the invaluable work that Evan performed for us in the electro-thermal simulation of induction heating in a furnace electrode arm. Okay, so a quick introduction to Metix. Metix is part of the larger German-owned SMS group. We have our offices here in Morningside, Santon, although to be honest, I haven't seen the inside of that office in a while. We share the premises with the local arm of the SMS group. Our core expertise is the design of pyrometallurgical processes and technologies, previously serving primarily the South African market. But with the integration into the SMS group, we've become the center of competence for the global submerged arc furnace technologies. Traditionally, the pyrometallurgy fits into the processing of minerals and ores. However, as there's been a global drive towards efficiency and reduction of waste, we've also seen an uptake of the application of these technologies to rework waste materials in order to recover whatever valuable commodities are left. So just a quick run through the agenda. I'll introduce the problem statement and then hand over to Evan, who's going to run you through the simulation setup, the results, and the conclusion. And then we will tie it all back together in the design changes, how we've incorporated the learnings from both the work that Evan and myself have done into to arrive at a mature design. Okay, so what was the challenge? Well, Metix was placed in the unenviable position of being handed a design for which we needed to take responsibility, but had absolutely no hand in designing in the first place. So after evaluating the original design, we came to the conclusion that there were inherent elements to it that made us feel uncomfortable. And we opted to adopt a more familiar design as found elsewhere in the SMS group. What this meant was that we needed to undertake a very, very accelerated due diligence on this revised design, and which is why we were infinitely thankful to be able to reach out to QFinSoft and to Evan in order to assist with this accelerated due diligence. So where does the arm and electrode mast fit into the bigger picture? Well, the application in this case is for a very, very small pilot scale tilting alternating current electric furnace. Only about 2.2 MVA, which sounds like a lot, but for electric arc furnaces, this is a baby. The furnace is only about 2.5 meters in diameter. And again, just to give you context, the typical ferrochrome furnaces in South Africa are the region of 14.5 to 15 meters. And on the circular furnaces, they can go up as big as 18 to 20 meters. The electrode arms are responsible for regulating the electrode position during operation, but also more importantly, or as important, to completely remove the electrodes in order to allow the furnace to tilt in the first place. They're traditionally constructed from water-cooled carbon steel, but in this case there wasn't an opportunity or the simplified construction did not afford the opportunity to water cool every element of the electrode arm. So what you see here is a bit of a breakdown, just so that you understand what we're talking about as Evan proceeds to run you through his exercises. So we refer to this front section as the sail, the mast, which ties up with these long vertical members over here. We have the current carrying bus tubes on either side, carrying 4.5 kiloamps each, if memory serves, the carriage, and then the rollers, which will become a focal point for this exercise. So even though we now had an electrode arm design that was more familiar to us, we were going to be operating at higher power levels than we had before, which meant that our understanding of the inductive heating effects were now to be questioned. We did consider completely mitigating those effects by fabricating the electrode arm from austenitic stainless steel. However, at a cost factor of roughly 3 to 1, this quickly became a last resort as opposed to a first option. So in order to guide our decision making, we needed to quantify these heating effects. Instead of bringing all these activities in-house, the time constraints of the project forced us to make the strategic decision to split our activities, divide and conquer, so to speak, where I would tackle the structural FEA component of it, and QFinsoft, aka Evan, would tackle the thermal electric modeling of it, with the idea that whatever lessons we learned from the thermal electric modeling could be incorporated into the final design in such a way that we would mitigate any excessive heating effects that may compromise the mechanical strength of the carbon steel.
Right, and taking those simulation goals into account, where we have the temperature rise coming from electromagnetic field, we need to combine the two different physics together. So this means we'll need to couple together two different software packages. So for the electromagnetic field, we'll be looking at ANSYS Maxwell, and then for the temperature distribution, we'll use ANSYS Mechanical to calculate that. And when transferring information between two different physics, you can either have a one-way coupling or a two-way coupling where information is transferred back and forth a number of times. But for this particular application, we thought that a one-way coupling was sufficiently accurate. So in discussions with Metix, there were a couple of different design options that we wanted to look at. So the initial one was the original design, which is just a full carbon steel construction, which is the cheapest option, but also the most likely to have problems with high temperatures. And then the other case was one where we would actually put an aluminium plate in there to shield the carriage from the electromagnetic field of the bus tubes. And thought that was quite a simple but very effective option, so we decided to look at that. So in Maxwell, fairly straightforward eddy current design type. So this is where we can specifically look at the induction losses in the components, and by nature that is a static simulation. Even though we are using an AC current, the final result is essentially a static result. So you can see we have quite a high current there at 50 Hertz frequency. And we've got two bus tubes bringing current in, but the current in one of the bus tubes is 120 degrees out of phase with the other one, so we could set that up in the boundary conditions as well. And then we included solid conductors, just that'll affect how the losses are generated in the bus tubes. And then what's quite nice with the electromagnetics packages is they make use of adaptive meshing. So this makes meshing significantly easier and a lot less effort. But we did add some manual refinement in the arm and rollers just to make sure we got the fidelity we required in those areas. And then the adaptive meshing does focus around the frequency of our simulation. So the 50 Hertz of the current is what we adapted around. Okay, and you can see here on the right are the materials we used. So for the arm was just a simple carbon steel, bus tubes were made of copper, and then the aluminium shielding panels for the second design case. Right, so looking here, at the results, we can see these contours of the magnetic flux density, or the B field as they call it. So we can see on the left here is the results for the 0 degrees phase current, and on the right-hand side is the current for the right-hand bus tube, which is 120 degrees out of phase. So we can see sort of identical fields, obviously, but in their respective phases, each one impacts on the carriage. And then the final result we'll see will be a combination of these. But you can see here that the field is very focused around the bus tubes, and it interacts quite strongly with the surface of the carriage. Okay, so this is a cut plane through the center of the mast and the carriage. So you can see the mast is running vertically here and the rollers across here. Okay, so you can see that there's quite a strong interaction with the field and the surface of the carriage, the arm. Looking now at the other end of the arm, so this is the sort of tip of the sail. You can see that the bus tubes are below, but still very close to the arm, and there's a very strong interaction here between the bus tubes and the arm, which we'll see the results of on the next slide. So this plot here shows the ohmic loss within the arm component. So ohmic loss is a measure of the energy loss due to the induction heating, or the eddy current effect, should I say. And you can see here that in the carriage, there's quite a strong interaction between the bus tubes and the carriage. We get quite a large ohmic loss in that region. And this region is sort of closer to the upper rollers. So we expect to see much higher temperatures in the upper rollers compared to the lower ones. And you can see here that the major loss within the arm from the ohmic loss is actually at the end of the sail, where the bus tube is running very close to the mast component there. And a similar plot now, but focusing on the mast and the rollers, just to have a look and see how they still also have a noticeable ohmic loss term in those components. So expect some heat to come from there as well. So when we now move to do the thermal analysis, as I said, there's a couple of different ways to do it. For those who aren't aware, the last few releases of the electronics desktop have actually included a mechanical design type within the desktop. So you can see here within your, you've got your Maxwell design types and your HFSS and all of that. And we also have an option for mechanical there. So within the electronics desktop, we can do some basic thermal analysis, and we can even do a modal analysis of our components. And basically, this just makes it so much easier to move from our electromagnetic simulation to structural, or essentially a physical structural model without actually having to go into another package. Okay, so we can do our model from a thermal point of view. We can model conduction and convection within our components, all staying within the electronics desktop. The only limitation for the thermal side is that radiation is not currently supported, so we couldn't include that, and you'll see that that becomes important later. So we have to move away to a different method. But just to highlight how easy it is to work with this mechanical design type within, we just a slide here just to show we do our electromagnetic simulation. We bring in our mechanical design type. We select the components that have the heating loss. We assign an EM loss excitation to those components. We link it to our Maxwell design through this window. We scope it to the different objects, and then we end up with an EM loss term as one of our boundary conditions. So within a few clicks, we easily set up a thermal simulation from our electromagnetic. Okay, so for those of you who are doing some basic thermal analysis, just bear this in mind that this is an option for you to use. But as I said, rate will show to be important. So we had to make use of Workbench Mechanical, the full mechanical solver. So we went into Workbench, we brought in our Maxwell model there, we linked it to a steady state thermal component system, and then we could add both convection and radiation boundary conditions to measure heat loss from both those methods. And then you can see our imported heat generation here coming from Maxwell, which is essentially just a drag and a drop within the Workbench environment. And then because we're in mechanical, all the usual post-processing options are available there. So if we have a look at this table of temperatures, so we'll see why the different types of heat loss are important. If we look here in the first column, we see that if we just look at the heating due to the eddy currents, we'll see that we end up with very large temperatures. These are extremely large, and the material is virtually going to melt at this point, so it's just not practical. But if we now include heat loss through convection, we get a significant drop in the temperature. And then if we include radiation, we get an even further drop in the temperature there. Okay, so in this case, showing that both convection and radiation are very significant mechanisms for losing heat from the system, and we do need to include both of them. Okay, so I mean the significant drop from convection is most likely due to the large surface area and small thickness of the material used in or at least in the arm and the mask material. And then obviously radiation, we sometimes ignore, but can actually be quite important, especially when there's a large difference between the heat of the components and the surrounding area. Okay, so this just proves that we need to consider all the different types of heating and heat loss, because they can be quite important. And certainly from a simulation side, that's why we say it's always good to try and understand the physics that are at play in your model, because if you don't include the different physics, the software is not going to know to do it for you. So, either you need to include it beforehand, or maybe do a bit of a trial and error and see, like we did here, what is the significance of adding these additional physics. And then if we look at the temperature plot for this case, in this case for both the convection and the radiation, we can see that the peak temperature in the carriage area is about 90 degrees here, obviously where the bus tube runs near to the carriage. But the highest temperature that we measured was actually down here at the end of the sail, at about 166 degrees Celsius. And imagine, just because there's far less material, the bus tubes are running even much closer to the arm, so we to get a much larger heating effect in that area. Okay, and on the right here we see the temperature distribution within the mast, and we can see that obviously temperatures are much lower, but heating from the mast itself, as well as conduction coming from the rollers, and that will heat this area up significantly. And you can see here we have a much higher temperature in line with where the bus tubes would run across the carriage. Right, so then moving on to the second design, we want to do, now that we've got a base case to compare with, we looked at adding aluminium plating between the carriage and the bus tubes. So this is a plate same size as the carriage and about 10 millimeters thick, and it's situated halfway between the carriage and the bus tubes. All right, so we wanted to see, this is quite a simple fix, and we wanted to see how effective this would be in reducing temperatures within the rollers. So if we look now at the B-field plots, on the left-hand side we see the B-field contour plot for the design with shielding for case 2, and on the right-hand side we see it for the option where there was no shielding, just so you can compare the intensity of the field, and you can see quite dramatically how this, just a simple aluminium plate, really just blocks off the field from reaching the carriage. So there's a strong interaction between the bus tube and the aluminium plate itself, and that prevents the field really from passing past the plate and to the carriage. Okay, so you can see just even visually we get quite a significant shielding effect there from these plates. All right, and if we look at the ohmic loss within the mast or the arm, you'll see here that in the area where the bus tube runs close to the carriage, we get quite a significant reduction in the overall ohmic loss in that area. But if we look down at the end of the arm, where there is no shielding and where the bus tubes run close to the arm there, that we still get a similar loss as before. Okay, so we can see that there's a very localized effect from the shielding. So that's something we really need to take into account moving forward with this design. We look at the temperature plots as a result of that. We can see that here on the carriage area, we get as you saw with ohmic loss, there's a significant reduction even here in the region where the bus tubes run across the carriage. And if we look at the end of the mast there, where there's no shielding and the bus tubes are running across, we're getting essentially the same temperature as before. Okay, so just really again highlighting how localized the effect of the shielding is. So now if we have a temperature comparison, so if we look at the table here at the bottom and compare the temperatures from case 1 to case 2, we can see that especially for the top rollers, there's quite a significant drop in the temperature in the rollers. Even the bottom rollers to still see some reduction, maybe not as much, but they do see a drop in temperatures, which is quite a good thing. And we can see now that the roller temperatures are on a much more favorable operating temperature, which would mean that the bearings and that in the rollers would be much more reliable. Okay, so that's quite a positive result from this design, but obviously we just need to take into account that the shielding effect is very localized. So just to conclude, as we saw, the original design had quite a high resultant temperature from the induction heating, 165 degrees, and the carriage area was about 90 degrees. And this obviously meant that the roller temperatures were far too high for normal operating, being up to sort of 85 degrees or so. And so, we did need to find a way to kind of mitigate the heating from these cases. And this is where we brought in the aluminium shielding, which made quite a significant difference to the temperature in the carriage area. But obviously, moving outside of the shielding was very localized, and moving outside of that, we still ended up with the same temperatures as before. Okay, so quite a nice sort of result from this, showing that quite a simple change can make quite a difference to the operating of this design. And I thought I'd just, before Phil talks a bit more about the final design that we went with, I just thought I'd throw in this quote here from one of Phil's colleagues, Brett Alford. He says, "Thank goodness we did the simulations, because the rollers in particular may not have had an adequate lifetime or would simply not have worked." And this really just drives home the importance of simulation and why we offer simulation as a design tool, because it really just allows you to look at different design options before you even go ahead with the design, spot any issues that might cause some downtime or something like that, and you can really sort of optimize and improve the design to reduce cost and downtime before you even build the thing. So I just thought that summed up the project very nicely. Right, so thanks for your time. I'm going to hand over now to Phil, who's going to just talk a bit about the final design that came about as a result of the findings of this project. So I think that'll be quite a nice way to just sum up this work, and again, just highlighting the sort of the design tool and the handiness of doing simulation work. So thanks, Phil. Over to you.
Thank you, Evan, for that intelligible presentation and conclusion. I'm sure, as most of you who work with the software on a daily basis will agree, the real simulation work seldom goes as smoothly as is portrayed in these presentations. So on the right hand side, we have the culmination of the thermal, electric and structural FEA work. On the structural side, we see a geometry change on the sail, and this was done to increase the vertical stiffness in order to reduce the tip deflection, which gets amplified as a consequence of the length of the electrode. We also see the addition of gussets on both sides of the sail in order to increase its lateral stiffness. And what is not quite so obvious in this picture is the addition of small box sections on the carriage in order to help with the distribution of the forces. On the thermal electric side, the efficacy of the shielding cannot be denied. However, the possibility to implement that along the full length of the sail was limited, so instead we chose to eliminate the problem entirely by raising the bus tubes. It did come with the trade-off of longer bus tubes, which had a marginal cost implication, but it was considered to be worth it. However, proximity to the carriage and the topmost rollers could not be avoided, and as such we are left with a much smaller but still very effective shielding at the top to protect those elements. Metlix would like to again extend our gratitude to QFin Soft and specifically to Evan for the role that they played in maturing this electrode arm and assisting us in what felt like a very, very frantic short period. Thank you to everyone for listening today.